4.57, we have this graph, and we have three different elements, A, B, and C, and it gives us the first, second, third, and fourth ionization energies for those three elements. So the key thing to look for here is which of those ionization energies is much higher than expected or lower than expected, because we know that when we're looking at ionization energy or electron affinity, if the element has an exact noble gas configuration, electron configuration, then it should be stable, right? So the exact same number of electrons as one of the noble gases should make the element stable. So if it's stable and it already has that number, then it's going to be difficult to pull one out or put an extra one in. So in that case, we would have a higher than expected ionization energy and lower than expected electron affinity. Right, so if it has a stable number of electrons, it doesn't want to let one go and have one be pulled out and be ionized. It also doesn't want to pick one up, so its affinity for a new electron is very low. And so then we could say the opposite of that. If an element can make an exact noble gas configuration, an electron configuration, by adjusting the number of electrons by only one electron, then it will be very easy to do that. So if we're talking about ionization energy, we're talking about losing one electron. So that would be a very low ionization energy expected. If we're talking about one away from a noble gas configuration and I need to add an electron in to make that configuration, then I'm talking about electron affinity. So that would be a very high electron affinity. So this example 4.57 illustrates that. So if we look at the graph there, it has it plots the ionization energy versus the ionization number, which is really the number of electrons that need to be removed. And so the first ionization, or the removal of one electron for all of those elements, is really low. So they're all pretty similar there. If we look at element A, so all of their ionization energies will go up when I get to the second ionization energy, right? Because when I have to take one electron out, I have to overcome whatever attraction that electron has to the nucleus. It's going to be a valence electron, so there's going to be some other electrons in between causing shielding and a little repulsion. But whatever that valence electron is, I'm going to remove it, and it requires some energy to overcome its attraction to the nucleus. Once I remove that electron, when I think about removing a second electron, now the second electron is going to be more difficult, always. Because when I remove the first electron, the remaining electrons, there are fewer of them and they repel each other a little bit less. So with less shielding between them, they can all get a little bit closer to the nucleus, and that creates a greater effective nuclear attraction for those remaining electrons. So it's harder to remove the second one. So if you look at that graph for A, so on the in the question in the textbook, they're all plotted on the same graph. I'll plot them one by one because I don't want it to look too cluttered. But for A, looking at A, which is the blue triangle, it goes up a little bit. It goes up a little bit more. No major jumps here. Nothing really big to look at. And then the fourth one is really much bigger than the first two. So when I see a larger than expected ionization energy, that suggests that after the third one was removed, this jump here occurred when a noble gas configuration was broken up. So that means this data is suggesting that to knock the first electron out, I have to overcome a little energy. To knock the second, a little bit more energy to overcome the attraction. One more, just a little bit more energy to overcome the attraction in the nucleus. But then once I get to this point, this must be a relatively stable nucleus, because to knock another electron out of that, it takes a lot more energy. So that means this is probably an element that will make a noble gas configuration after I knock 3 electrons out. And if I were to knock a 4th electron out, that would break the noble gas configuration. Right? So again, the noble gas configuration only affects these energies when I'm either at a noble gas configuration or when I break the noble gas configuration. So for that element, let's see, what does it say exactly? The group number. So we want to know what column that element is. So that should be here. Scandium, deuterium, etc. This column and one of these two. Scandium, actinium. If I take one electron out, it doesn't take too much energy. Take another one out, it doesn't take too much energy. Take one more out, I make the same number as the noble gas. Also, not much energy. But then now I've got a stable arrangement. If I want to remove a 4th electron, it takes a lot of energy. Right? So that noble gas configuration is what makes it stable. So the answer for A should be this column here, which would be 3B, I guess. Or is that called 1B? I don't know. Whatever column that is on your periodic table. So that's A. For B, we're looking at the red squares. So just get rid of this for now. So if I'm looking at the red squares. For that one, the biggest increase is the first one. So the first electron removed doesn't take much energy. The second electron removed is like up here. That required a lot more energy than was to remove the second electron from A. Oops, I'm looking at the wrong question. Dang it. Forget I said that. I was looking at 4.56. 4.57. B is even lower. B is a red triangle. So to remove the second electron from B, very little energy. And then the third electron is where the big jump is. And then the 4th electron, a little bit more energy, not much of a big difference. Okay, so in this one, for B, it's suggesting that a little bit of energy to remove the first electron, a little bit more energy to remove the second electron, and then that is what got us to a noble gas configuration. Because once we get there, if we want to keep removing another electron, it takes a lot more energy. So that is suggestive of column 2A. Because if I'm dealing with any of these atoms like barium, not much energy to remove the 56th electron to go down to 55. And now it takes very little energy to increase beyond that to go to the noble gas configuration. But once I'm here, to remove the third electron, a lot more energy. So that's basically how you do that. And then for C, C is the one where the large jump occurs upon removing the second electron. So for C, it's easy to remove the first electron to get to the noble gas configuration, but once you're there, it's very difficult. It takes a lot more energy to remove the second electron. So that would be the elements in group 1A, excluding hydrogen, because hydrogen only has 1 electron. Questions about that? Other questions? So the question is, why does the atomic radius change from right to left? So if you stay on a horizontal row and you're asked about what's happening with the atomic radius, what you want to focus on are the factors we talked about. So for size, the two factors are shielding and number of protons. Right? Those are the two factors that affect the size of an atom, the ones that we talked about. So if you're on a horizontal row, all the elements in that row have their valence electrons in the same energy level. And so I just pick any row, go to the left of the row, and that number tells me what energy level the outermost electrons are in. So potassium, calcium, scandium, etc., all across this row, gallium, arsenic, selenium, all these elements in row 4 have their valence electrons in the 4th energy level. Whether it's the 4s or the 4p, it depends on the element. But all of these have at least one electron in the 4th energy level and no electrons in the 5th energy level. So that makes the 4th level the valence level. So when we talked about the factors that affect size, the priority, the factor that we look to first, is shielding. So if I'm comparing two elements that have their outer electrons in the same energy level, they should have very similar quantities of shielding. Ultimately, elements will only have equal shielding if they have equal numbers of electrons. So if I'm comparing like arsenic with calcium, arsenic and calcium, calcium's valence electrons are in the 4s, arsenic's valence electrons are in the 4p. So those both have 4 levels of electrons, and the first 3 levels are doing the majority of the shielding. Since arsenic has extra electrons in the 4th energy level that calcium doesn't have, it does have a little bit more shielding, but the majority of the shielding is done by the core electron. So since calcium and arsenic's valence electrons are in energy level 4, that means their core electrons on the first 3 levels, they should have similar quantities of shielding since they have shielded primarily by the same core levels. So if they have similar quantities of shielding, then we look to see which has more protons. So an element with 20 positive charges versus an element with 33 positive charges, that makes a big difference. Normally the shielding is a bigger factor, but when the shielding is similar because their valence levels are the same level, then we go to the number of protons. So to answer your question, as you go from right to left, the shielding isn't changing much, but every time you move to one element to the left, you take away some of the positive charge in the nucleus, so it attracts the electrons less effectively and they don't get pulled in as tightly until it's larger.